I'm Bob Duhamel, and I'm developing a class on relativity based on Einstein's book. And as usual, I'm trying to break this down and explain it in a way that you and I can understand it. And as I go through this process, I'll make occasional videos to show you how I am doing this. And one of the things you encounter in relativity is length contraction. And here is the Lorentz transformation as used to calculate length contraction. So when you see an object moving, it is shortened in the direction that it is moving, and this formula calculates how much it is shortened. So the length at a certain velocity is equal to the square root of 1 minus the velocity squared over the speed of light squared. Now, math is not my strength by any means, but looking at this formula, I think that looks an awful lot like the Pythagorean theorem. And here is the Pythagorean theorem over here, which is used to calculate the hypotenuse of a right triangle when you know the adjacent and the opposite. So the hypotenuse is equal to the square root of the adjacent squared plus the opposite squared. And I Googled it, and I saw some websites that said, oh yeah, the Lorentz transformation is related to the Pythagorean theorem, sort of. But the more I looked at it, the more I think that is the Pythagorean theorem, just massaged to find a different result. So I decided to see if I could prove for myself using basic algebra that the Pythagorean theorem is the same formula as the Lorentz transformation. So once again, the Pythagorean theorem is used to calculate the hypotenuse of a triangle if you know the adjacent and the opposite. But in the case of length contraction, you're trying to find the length of an object based on its speed in relation to the speed of light. So let's see if we can re-express this as that. So another way to express the Pythagorean theorem is the hypotenuse squared is equal to the adjacent squared plus the opposite squared. Now actually, what we want to do is find the length of the adjacent if we know the opposite and the hypotenuse. So what I'm going to do is just use some simple math to find the adjacent based on the hypotenuse and the opposite. So the adjacent squared is equal to the hypotenuse squared minus the opposite squared. Looks like we're already going in the right direction, doesn't it? But I also want to find the length of the adjacent as a decimal fraction of the length of the hypotenuse. So what I need to do is divide the adjacent by the hypotenuse. So the adjacent squared is divided by the hypotenuse squared, and I have to divide everything else by the hypotenuse squared too. So the hypotenuse squared is divided by the hypotenuse squared minus the opposite squared over the hypotenuse squared. Now, another look at this, we see that this term here is the hypotenuse squared divided by the hypotenuse squared. We know that's 1. So that brings us to the adjacent squared over the hypotenuse squared is equal to 1 minus the opposite squared over the hypotenuse squared. It's looking more and more like that every day. So now if we take the square root of that, the adjacent squared over the hypotenuse squared equals 1 minus the opposite squared over the hypotenuse squared. We're going to square root that, and that's going to give us the adjacent over the hypotenuse is equal to the square root of 1 minus the opposite squared over the hypotenuse squared. That is looking almost exactly like that. The only difference is we have the adjacent over the hypotenuse here. But we want to get our number in a decimal fraction, and that's what this will give us. So we divide the adjacent by the hypotenuse. That'll give us a decimal fraction of the length of the adjacent compared to the hypotenuse. So let's go ahead and take these terms and move them over here. So the adjacent over the hypotenuse now becomes the length at the velocity. So that becomes that term. The opposite becomes our velocity, and the hypotenuse becomes the speed of light. So there we have the length at a certain velocity is equal to the square root of 1 minus the velocity squared over the speed of light squared. And we see that that is actually the Pythagorean theorem. Now I've read that the Lorentz transformation actually uses hyperbolic math. There's no hyperbolic math here. It's just plain Euclidean geometry to calculate that out. Now, if we plug the numbers into the formula, we can actually develop these triangles. These are just 3 examples. When we do this, the hypotenuse represents the speed of light. The opposite represents the object's speed, and the adjacent becomes the decimal fraction of the length of the object at speed compared to its length at rest. So here we have the speed of light, the object's speed, and then the decimal fraction of the length. So we plug in the numbers. Here's the speed of light. There's half the speed of light. Going at half the speed of light, we find that the length of the adjacent is 0.866, and so the length would be 0.866 times the length at rest. At 0.707 times the speed of light, we hit a sweet spot where at 0.707 times the speed of light, our length contraction factor is going to be 0.707 times the length at rest. And here at 90% of the speed of light, so here's the speed of light, there's 90% of the speed of light, creates this triangle, and we find that our length is 0.435 times the length at rest. And these numbers work with that formula, and we can confirm them with the Pythagorean theorem that the Lorentz transformation for the length contraction is simply Euclidean geometry. A derivative of this formula is for time dilation, and time dilation, we don't talk about the contraction of time, but how much longer it takes to reach a certain amount of time. So we're looking at a clock going slower when it's moving, and so it takes longer from our perspective to go through a certain amount of time. So we take the reciprocal of this formula to find time dilation. But if we take the reciprocal of that, we get the percentage of time that the moving object goes through compared to the time we've gone through. So if I'm watching a moving clock and I watch it for a certain amount of time, I will see it tick off less time, and it would be exactly the same as this. So if that clock is going at half the speed of light, when I see a minute tick off, I would see that other clock tick off 0.866 minutes. And of course, if that clock is moving at 0.707 times the speed of light, after I see 1 minute go by, I will see that clock tick off 0.707 minutes. So you can use the same formula for time dilation if you use it in that manner. But to find the time dilation where we're looking at how much longer it takes for that clock to reach a certain point, then we would take the reciprocal of this, which gives us a factor called gamma, which is used in a number of equations related to the Lorentz transformations. So there's an explanation of length contraction where, yes, this math confirms it, but we can visualize it by making right triangles. So as our speed increases, the opposite becomes longer, which pushes the hypotenuse at a higher and higher angle. Once again, the hypotenuse is the speed of light. The opposite is the object speed, and then the adjacent is the length contraction factor compared to the original length, which would be that length there. Another thing I discovered, if we use the same geometry to calculate time dilation as I explained we can, then the length of this line here, which is the same length as the speed of light, implies that we are moving through time at the speed of light. And I thought about this. Okay, that length is the same length as the speed of light, but that represents going through time, and the full length of that represents my time, and the decimal fractions represent the time that the other object goes through. Is that saying that we are moving through time at the speed of light? Well, I looked it up, and sure enough, if you do the math, I haven't done the math myself, but I've seen it explained, where after you finish off, you end up with the speed of light representing our speed through time. So we are passing through time at the speed of light, which means that in that dimension, we must be massless, because only a massless object can move at the speed of light. So in three-dimensional space, we have mass, and we cannot move at the speed of light. But in the fourth dimension, we have no mass, and therefore, by even existing, we move instantly at the speed of light, just like light does the same thing. It simply, by existing, moves at the speed of light. There are other implications I haven't figured out. For example, do we move a particular direction through time, or do we expand through time? It's something I haven't looked into, and I'm going to look into that and see what the physicists think. But anyway, I have discovered that the core formula for the Lorentz transformations is actually just the Pythagorean theorem rearranged to calculate the decimal fraction of the length of the adjacent compared to the hypotenuse, and that if we plug in these terms, that becomes the Lorentz transformation. I forgot to mention why I had the numbers in parentheses around the triangle, the 4, the 3, and the 5. This is because these are numbers that make it really simple to prove these theories in your head. The 3, 4, 5 rule is used by carpenters to make something square when they're building something that needs to be square. So if we have the adjacent is 4 units, such as 4 feet, and the opposite is 3 units, such as 3 feet, then the hypotenuse, if we have a right triangle, will be 5 units or 5 feet. So 3 squared is equal to 9, 4 squared is equal to 16, and 5 squared is equal to 25. And so we can go through the Pythagorean Theorem, where h squared equals a squared plus o squared. So the square of the hypotenuse is 25, the square of the adjacent is 16, the square of the opposite is 9, so we have 25 equals 16 plus 9. So we take the square root of 25 and we get 5. So there we have the 3, 4, 5 rule. 3 squared plus 4 squared equals 5 squared. Now if we take the Lorentz transformation and do the same thing, here is the derivative I made where a over h equals the square root of 1 minus o squared over h squared. Well, of course, we want a over h to be expressed as a decimal fraction. So the next formula we have 0.8 equals the square root of 1 minus 9 over 25. So 0.8 is the decimal fraction length of the adjacent, 9 is the square of the opposite, and 25 is the square of the hypotenuse. 25 into 9 to get 0.036, so now we have 0.8 equals the square root of 1 minus 0.036. And so we subtract 0.036 from 1, so now we have 0.8 equals the square root of 0.64, which is correct. So this shows that the core equation of the Lorentz transformation is actually the Pythagorean theorem. So if you found this interesting, give me a thumbs up, really helps the channel. Don't forget to subscribe, hit the gray bell when you do. And as always, a big thank you to my patrons and channel members and other donors. I could not make these videos without your support. And thanks to everyone for watching.